Lesson 4, using notation to describe rules. Okay, so we have our learning targets. And our learning targets say that I can make sense of rules of functions when they are written in function notation. So I can make sense of the rules when I see it in function notation, and I can create tables and graphs to represent those functions. Also, I can write equations that represent the rules of functions. So let's get into it. First, make sure this is in your notes. Don't forget, anytime the video gets going too quick, just press pause and catch up. So what do you notice and what do you wonder? We have two different functions. So what do you notice? For one thing, it says x and f of x equals this rule. And then over here, it says x and g of x equals this rule. As opposed to input and output, or as opposed to x and y, right? This is written a little bit differently, right? Your input is x and your output represented as f of x. And since there's two different names, the f function and the g function, apparently we are dealing with two different functions. So far you should have this in your notes. The tables do not say input and output or x and y. That was one of the things I had discussed. We also said that one was called f and the other has g. So now we have names for these functions. It's also important to notice that an expression rather than a number is on the right side, right? So we have this expression over here on the right side. And what we know is if we substitute the x values, right, of the left column into the expression, we'll get the right column. What I mean is if you put 1 into the x value right here, so if we put 1 in this, we could say 10 minus 2 times 1, well, 2 times 1 is 2, and 10 minus 2 is 8. What happens if we move down the column and we use, say, 5 as the input? Right, so we'll take this out and we'll put in 5 here. Well, that's 10 minus 2 times 5, which is 10 minus 10, which is 0. So 5 yields an output of 0. Over on the right side, if you take 3 as an input, and you put 3 right here, 3 to the third power is 3 times 3 times 3, which is 27. So it's still, we're still able to build a table like we used to. So you want to think about functions like a machine. I always say like a soda machine, right? You put some coins in, you press a button, and out comes a drink. So we have the input goes into the rule, and the rule in this function machine is to cube the input, right? And to cube the input means we're going to raise it to the third power. And then that produces an output, right? So find the outputs when 0, 1, and 3, and x are the inputs. Well, 0 raised to the third power is 0 times 0 times 0, which is 0. 1 raised to the third power is 1 times 1 times 1 is 1. 3 to the third power, as we just said, was 27. That's 3 times 3 times 3, which is 9 times 3, which is 27. And then x to the third is simply x to the third power. So we have our inputs, 0, 1, 3, and x, and our outputs. First is expressed as a rule, or as in function notation rather, g of x, and that output is x to the third. And by the way, this was the same function as the second table in the intro. Okay, so here we have several functions here on the left side. We got the f of x, g of x, h of x, and k of x. And they all have rules over here involving 3's, x's, and 7's. Over here, we have a series of descriptions. And what we want to do is we want to match the description to the function. So first, we'll take a. To get the output, right, what we're going to do is subtract 7 from the input and then divide the result by 3. Now, if we want to subtract 7 before division, then the subtraction needs to be housed inside of parentheses, or at least implied parentheses, which is what we have on this k function. So a goes with the k function. Next, b. To get the output, we're going to subtract 7 from the input and then multiply by 3. Again, if you're going to subtract prior to multiplying, then it needs to be housed in parentheses. So b must go with g. For part C, to get the output, multiply the input by 3, then subtract. So we're going to multiply prior to subtraction, which is our regular order of operations. So that is going to look like your regular piece, multiplying by 3, then subtracting by 7. Notice the difference, right? Subtract by 7, then multiply. Oh, you have to house that inside of parentheses in order to have the subtraction supersede the multiplication. But when we want to do regular order, just no parentheses is necessary. C goes with our F function. Therefore, D must go with our last one. But we just want to verify it by reading it and making sure, because we could have made a mistake. So let's just make sure that we agree that it goes with it. To get the output, we are going to divide by 3, right? And then subtract by 7. So the subtraction has to come after the division. Over here, I would do the division first and then subtract by 7. As opposed to this, there's implied parentheses on the top. I would subtract by 7 and then divide by 3. So it looks like CBDA is our order. So far, we have matched the equation with a verbal description, and we've recorded our results. For number 2, it says for one of these functions up here, when the input is 6, when I put 6 in for x, the output is -3. Which function is that, and how do you know? Well, one way to go about this would be to put 6 into each function, and when we get -3 out, that's how we'll identify it. I mean, I suppose you could put these functions into Desmos, build a table, but it really takes too much time. We could do this by hand very quickly. So our first function is the F function, and so we're looking to use an input of 6, or in function notation, we're going to say f of 6 equals 3 times 6 minus 7. 3 times 6 is 18 minus 7. 18 minus 7 is 11, which is not -3. So I guess it's not that function. So we move on to the G function. G of 6, notice how I write it. That's how you should have it in your notes, right? Make sure you're writing your notes in proper notation. And we're going to put 6 in for x. And so that means that we have to do our subtraction first. So 6 minus 7 is -1. And 3 times -1 is -3. I think it's the G function. But I'm going to check the other ones just to make sure I didn't make any errors or that there wasn't more than one answer. That's possible. For the H function, H of 6 is going to be 6 divided by 3, which is 2. I'm going to do the division first. Minus 7, we get -5. So it's not the H function. And for the K function, we're going to say K of 6, so we're putting 6 in for x. Remember, this is implied parentheses, so I have to do the subtraction first, which is -1 over 3, which is -1/3, which again is not -3, so it's not the K function. The G function was the correct answer, and just for the record, it did say which is, and is singular, meaning that there is, or implying that there is only one answer. Again, you should have all 4 in your notes. Last question here says, which function value, f of x, g of x, h of x, or k of x, is the greatest when the input is 0? What about when the input is 10? So again, we're just going to evaluate all of these. So very quickly, f of 0 is going to be 3 times 0, which is 0, minus 7 is -7. G of 0 is going to be 0 minus 7, which is -7. Times 3 is -21. H of 0 is going to be 0 divided by 3, which is 0, minus 7 is -7. Oh, we've had that twice now. And then K of x, or K of 0, I should say, is going to be 0 minus -7, which is minus 7, which is -7, over 3 is -7/3. Now keep in mind that that is also a -2 and 1/3. Sometimes it's easier to look at as a mixed number to compare. So in terms of, which one is greatest when 0 is in, well, let's see here. I think 0 would be the smallest negative number, right? So I think that the K function, right? So when the input is 0, K of x is the greatest. What about when we substitute in 10? Well, 3 times 10 is 30, minus 7 is going to be 23. Down on the G function, 10 minus 7 is 3, and 3 times 3 is 9. On the H function, 10 divided by 3 is 3 1/3, and 10/3 minus 7, technically, again, is -11/3, but as you look at this as a mixed number, right, that would be 3 1/3, and 3 1/3 minus 7 is negative 3 2/3. So let's just say that this is negative 3 2/3. A little easier than negative 11/3. And then k of 10, our k function, 10 minus 3, or 10 minus 7 rather, is 3, and 3 over 3 is 1. So which one of these values is the greatest? It looks like the f function. So f of x would be greatest. Or technically, f of 10 is the greatest, and then we have k of 0 is the greatest. Again, to evaluate these, all we're doing is just substituting in values and seeing who wins. Now we move on to rules for area and perimeter. Now just remember, as we talk about area talks about the two-dimensional space that is inside an object or a polygon or a circle. And perimeter, right, is going to be the distance around, right? So perimeter is distance, that's one-dimensional. Area is two-dimensional. So when I say two-dimensional, I mean like square inches, square miles, versus over on singular dimension, you would just be inches or miles. And if we were talking about volume, volume is 3D, it would be cubic inches, cubic miles. Okay, let's move on. A square, so we're talking about a square that has a side of 9 centimeters has an area of 81 centimeters. The relationship between side length and the area of the square is a function, certainly. They want us to complete the table with the area for each given side length. So they gave us that 9 as the x, right? F of x became 81, where side length is our x and area is our f of x. Or perhaps we could call this the a function for area, right? So a of x, capital A. So you should know that the area of a square is equal to the side length squared. So 1 times 1 is 1. 2 times 2 is 4. 4 times 4 is 16. 6 times 6 is 36. And s times s is s squared. So as far as completing the table, I believe that we have done that. It says then write a rule for the function a that gives the area of a square in centimeters when the side length is s centimeters. Okay. Again, I had written originally that area was equal to s squared. This is more of, a area formula. Now we're writing a formal algebraic rule. And so that rule is going to state that area is a function of side length. And so a of s is equal to s squared. The reason I knew they wanted me to write it like that is it said to use function notation. So we're all set. Again, remember, if I'm going too quick, just press pause and you can catch yourself up. So part B is a two-part question. Part 1 says, what does a of 2 represent in this situation? So what does it represent is part 1. And what is its value is part 2. Well, the value of a of 2, right? There's 2, and a of 2 is 4. So what is its value? Its value is 4. What does it represent? A of 2 represents the area of a square with a side length of 2. Again, a of 2 is the representative of the output. The input itself is 2. So what does a of 2 represent? It is the area of a square in centimeters squared, or square centimeters, when the side length is 2. A of 2 is the area of the square when the side length is 2. And its value is 4. Remember, this was a two-part question. Last part is they would like for us to, on a coordinate plane, sketch a graph of the function. So they want us to sketch in these values. Now remember, this is my x and this is my y. So this is my x and this is my y. All right, so we plot the coordinates as we see them. So we have 1, 1. So 1, 1 is probably right about just off the line there. 2, 4. So 2, 4 is going to be still kind of right there. 4, 16 is going to jump pretty quick. 4, 16. And then 6, 36 is going to be way up here. And so if we start from 0, 0, it looks like this is growing as a curve pretty quickly. And there's our sketch. There's the author's version if you wanted something maybe a little bit bolder, cleaner looking. But as you notice, it's pretty similar. For the perimeter conversation, we're going to talk about a roll of paper, right? And this roll of paper is 3 feet wide, something like the paper we would line the bulletin boards around the room with. So it's 3 feet wide, and then we can cut at any length. So what if we cut it 2.5 feet, right? So this distance was 2.5 feet. So we know it's 3 feet top to bottom and 2.5 feet left to right. At least left to right in this picture. What is the perimeter of the paper? Well, the perimeter is the length of all the sides. So that would be 2.5 plus 2.5 plus 3 plus 3. Or 2 2.5s plus 2 3-foot lengths. 2 times 2.5 would be 5, plus 2 times 3 is 6, which gives us 11 feet. So the perimeter would be equal to 11 feet when the width is equal to 2.5. Or I should say they refer to that as length. The width was 3 feet. So when the length is 2.5 feet and the width is 3 feet, we have a perimeter of 11 feet. Now it says, well, they want us to complete a table and then write a rule for the function. Well, we kind of had that rule, right? The area definition is twice the length plus twice the width. Now we already know that the width is 3, right? So our perimeter is always going to be 2 times the length that we cut it plus 2 times 3, which is 6. So we're always going to add that universal number of 6, that value of 6. And they want us to write this in function notation as a p function. So p of what? P of the length, because the perimeter of this is going to change depending on our length. So that's going to be 2 times the length plus 6. So all I did is I kind of figured out my rule, and then I'm writing it in official function notation, right? So this is the function that they asked me to create. Now I think it's easier to have the function, and then we'll evaluate it. Now that we're evaluating, we could see that p of 1 is going to yield us 2 times that value of 1 plus 6, which is 2 plus 6, which is 8. And then onward and upward. Now we could have worked our way through it like this, where we took our input of 2, put 2 on the lengths, 3 on the width, and added 2 plus 3 is 5, plus 2 is 7, plus 3 is 10, and yielded an answer like that. Or again, we could put 5 in for here and say 2 times 5 is 10, plus 6 is, 2 times 2 is 4, plus 6 is 10. I had 10 on the brain there. I prefer the function version. Now again, either way you look at it, for 6.3, we could say p of 6.3 is 2 6.3s, which is 12.6, plus 6, which is 18.6, or we could go round robin of the picture. 6.3 plus 3 is 9.3, plus 3 is 12.3, plus the 6 is 18.6. So that's our 6.3 value, 18.6. 11, put 11 here, 11 here. 11 twice is 22, plus the 6 is 28. And of course for L, we're going to have 2 times L, or for our length, plus the 6. And we have a familiar question. What does P of 11 represent? Remember, that's an output. They're talking about that value of 28. So, and again, what is its value? P of 11 represents the perimeter of the paper with a width of 3 feet and a length of 11 feet to have a perimeter of 28. Again, P of 11 is the perimeter of the paper in feet. When the paper is cut at a length of 11 feet, its value is 28 feet, technically. And again, we're going to draw a picture of this. So we're going to go for 1, 8, 2, 10, 6.3, 18.6. So 6.3, 18.6, kind of, I don't know, ish. and we're going to draw a line. And what does that line look like? Well, it's going to start off over here and go nice and in a linear fashion. Notice no curve. This is linear. One-dimensional pieces tend to be linear graphs. Two-dimensional pieces tend to be curves. Again, if you want the author version, very similar to mine, just minus any imperfections. So that's a wrap. Pretty harmless notes, right? Some functions are defined by rules that that specify how to compute the output from the input, right? Specify a rule. And these rules can be verbal, as we saw, or expressions and equations, right? So rules and words to get the output of a function f, add 2 to the input, then multiply. So if you're going to add first, you're going to put in parentheses and then multiply. To get the output of a function m, you're going to multiply the input by 1/2 and then subtract. So no parentheses, and then subtract the result. So that's why the result is on the right side. Again, you're not subtracting 3 from the result. Subtracting 3 from the result would look like this. This is subtracting the result from 3. So, what comes from what? The result is here and 3 is here. Depending on who is written first, changes the order of that conversation. Some functions that relate to quantities in a situation can also be defined by rules and therefore can be expressed algebraically. Now, just wanted to divert back up to the top here. This first part is also adding 2 and then multiplying by 5. So as long as it's in parentheses, this order is interchangeable. This one is not interchangeable, right? Order matters in subtraction. Sorry, kind of zipped past that a little quick. Now it says, suppose the function gives the cost of buying n pounds of apples at $1.49 a pound. We can write the rule as C of n, right? The cost of n amount of apples is equal to $1.49 times the number of pounds of apples to define that cost function, right? Turning that into words. To see how the cost changes, we can put this into a table of values and we can graph it and see that this graphical representation is very linear. And just for the record, Algebra 1, the course that you've taken, is also referred to as linear algebra often, because most of the stuff that you cover in Algebra 1 is all linear functions. We do cover some stuff outside of that towards the end of some courses, but in our particular case, we really focused on the linear side of things. Go ahead and put in a star at the end of your notes so I know you listened all the way to the end, and have a great day.